Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are in chapter 9, we are discussing phenomenological theories. So let's quickly recall what points we have seen. So Landau's phenomenological approach sidesteps the need to look at microscopic details of any problem. So it starts off by looking at possibly experiments, and from the experiments inferring some sort of emergent field that can represent the symmetries underlying the system. So the experiments are used to discover what the symmetries are, as well as what kind of emergent fields can represent those symmetries. And these emergent fields, which we called as phi in the last lecture, are taken as the degrees of freedom of the system rather than the microscopic degrees of freedom like the spin, etc. The next important point is to make sure that the field that we are choosing can transform nicely under the symmetry, and technically speaking we will say that phi carries some representation of the symmetry group. We can look at this in more detail later, and Landau's idea after that follows on to construct an energy function or some free energy density or some kind of energetics associated with this emergent field phi, and in doing this certain reasonable postulates such as analyticity and invariance under symmetry are enforced. And in choosing this Landau function, we also introduce into the Landau function certain dimensionless coupling constants, whose dependence is chosen judiciously so as to reproduce the phenomenology that we know is there in the experiments. So this is the main step. So we choose the Landau function so that certain phenomenological aspects of the problem are reproduced, and once we are done with that, we can derive the equilibrium free energy density and so on, which will be in the simplest Landau theory approach. It will be simply the minimum of the Landau function. The minimum value of the Landau function for a given set of parameters will determine the equilibrium free energy density if you wish, and then from the non-analyticity of that minimum value of Landau function, which is the free energy, you can infer critical exponents and all of that stuff. So this is the framework of Landau theory, and most importantly we saw that Landau theory is very powerful in that it can reproduce very rich phase diagrams such as that found in the Bloom-Emery-Griffiths model and so on. Okay. So far our discussion has focused on systems with discrete symmetries like the Ising symmetry, and the natural question to ask is, can we look at systems with continuous symmetry? And we have already done so once in one of the earlier lectures when we looked at superfluidity and so on. And natural question is, can we write down theories to look at phenomena such as superfluids and superconductors, right? So in this lecture what we are going to do is, we are going to explore the physics of systems with continuous symmetry, and we will see what progress we can make on this front. So let's just quickly look at some experiments, because after all, physics is about experiments, and so we will look at some experiments and gain some inspirations. So when I talk about continuous symmetries, I am not talking about things like translation and so on. That's not the kind of symmetry I am talking about. Those are what we call arena symmetries. We are talking about internal symmetries which are continuous, right? So we are talking about internal continuous symmetries. So examples of such systems with internal continuous symmetry are superfluids and superconductors. Let me very quickly remind, and Heisenberg magnets and so on. Not Ising magnet, Heisenberg magnets, where the spin on each ion can point in any direction, so to speak. So that has some continuous symmetry rather than up and down. So let's just quickly revise what we saw in the superfluids. In superfluids, we looked at the superfluid experiments, and we pointed out in a previous lecture that around 2.1 Kelvin, 2.2 Kelvin, liquid helium liquid helium made of helium-4 atoms, which are bosons. They seem to go into a new phase of matter called as the superfluid. And what you can do is you can do certain experiment to figure out how much superfluid fraction is there. Okay, so this is done by a beautiful set of experiments by Andronikashvili. And what is shown here is the superfluid density sort of grows as you reduce temperature below this lambda transition temperature. And so this looks very much like an order parameter. And we even argued that the symmetry of the superfluid is described by something called the U1 group, which is a continuous group. There is a sister problem, which is a problem of electrons interacting with each other, and maybe through help of phonons, etc., that we do not need to go into all those microscopics here. So what happens is the electrons can go into a new phase called as the superconductor phase, and what is shown here is the phase diagram of a superconductor. So there are three axes here. This axis is temperature, this axis is magnetic field, and this axis is the current that you are sending through the superconducting system. Okay, so what you see is that in the absence of any current or magnetic field, if I come down this line, I will have a transition to a superconducting state. Okay, and there is a more interesting thing. If you're if you're below Tc and then you increase the current, then you can actually have a transition out of the superconductor and you can go to what is called as a normal state. So there are all these phenomena that we know exist, right? And one of the great successes of Landau theory was to come up with a phenomenological description of superconductivity with a continuous symmetry, and this is why I am bringing this up. We will have more to say about this in the coming lectures, but today I hope that you have been sufficiently well motivated by these experiments to explore the physics of systems with continuous symmetries. So what is the key step that we require to model phenomena such as this? So what we have to do is we have to figure out what is the underlying symmetry. So for example, in superfluids we know it's U1, which is a continuous symmetry, or we have to look at experiments and figure out what is the continuous symmetry. And then associated with that continuous symmetry, we have to come up with an emergent field phi. Right? So these are the two things that we need to do. Okay, so I'm going to start by positing or assuming that some experimental data is available to us and we have zeroed in on some kind of continuous symmetry. And we are talking about continuous internal symmetries, as I said, right? So how do we, let's say that we have come up with this, and how do we describe a continuous symmetry in mathematical terms? So we know that continuous symmetries can be described by continuous groups that are like manifolds meaning smooth geometric objects, right? So what we're going to do is we're going to study a class of systems with different continuous symmetries. And the continuous symmetries that we are going to focus are what are called as ON continuous symmetries. What do we mean by ON? So they are represented by orthogonal groups, and this symmetry will be continuous whenever n is greater than or equal to 2, right? So I will have more to say in a moment. When n equal to 1, this is a discrete system and O1 is Z2. So you can see why we are interested in ON. There are very good physical reasons because there are many systems that will have O2, O3 symmetries. And also from an analysis perspective, O1 is Z2, so we can actually reproduce all the Ising results by simply putting n equal to 1, right? So that is also a certain advantage. Okay, so what is this ON symmetry group? So each element of ON symmetric group can be described by an n by n orthogonal matrix R, right? So this R is some orthogonal matrix which is n by n, and if you write down the components, you can write it as R alpha beta, where alpha and alpha gamma, where alpha and gamma run from 1 to n. So it's an n by n matrix. And the important condition of orthogonality is that R transpose R becomes the identity matrix. Identity is the n by n identity matrix. So if you write this in component form, you know that the identity matrix, its matrix elements are the Kronecker delta that you have. So it will be mu nu and so on. And so the orthogonality rule tells you that if I multiply these two R transpose R using this index notation, then you will get this identity matrix now written in component form using Kronecker deltas. So here just mind you that there is two repeated indices, and so we are using the Einstein summation convention. So unless I state explicitly in the notes as we go along, the Einstein summation convention will be used where repeated indices are summed over their range, right? So in this case from 1 to n. Okay. Now what we need is, we have identified a symmetry and we know how to describe the symmetry using matrices. So what we need is, we need an emergent field that can represent this, that can capture this symmetry. That means when I hit this symmetry operation on that emergent field, it will transform in a certain way, right? So this is what we need. And so there is a very natural candidate just around the corner, and that is an n component real valued vector. So okay, so this is what we call, so I'll just explain the notation here. There is a bold phi here. So when I write bold phi, I'm writing it as all the components are included. It's like how you typically write when you're writing on your notebook, you write phi and put a vector sign on it. So instead of a vector sign, I'm just using a bold symbol for that. And this is equivalent to n components of phi alpha, n components labeled by index alpha. Alpha goes from 1 to n. So how can the symmetry act on this? So you know that you give me any n by n orthogonal matrix and an n component vector, I can hit the orthogonal matrix on the n component vector and that will transform the vector, and that is exactly what I have done here. So if you give me phi alpha, I will hit this R matrix on the column vector of phi, and this will give me a new vector which also belongs to the same the n component vectors. So this is how the symmetry acts on my emergent field. So now you can see that if just make sure that we are following this along. So what are the 1 by 1 orthogonal matrices? So there are only two 1 by 1 orthogonal matrices, the number 1 and the number -1, right? And so you can see that if I stick to n equal to 1, R is either +1 or -1, and there's only one component. So either phi will go to phi itself, or phi will go to -phi. Phi going to phi is the identity operation, and phi going to -phi is the flip operation. So you can see that immediately you recover what you already know from our previous discussion within this framework. Okay, so good. So this is what happens. I want to paste a note of caution here. So typically when we start off, we may think that these alpha are some space indices. Like for example, you may think that alpha equal to 1 is like x direction, y direction and z direction, so on. So you must appreciate that this is not the case here. Alpha are directions in the internal space. So for example, if I could have a superfluid in 3 dimensions, but the superfluid is described by some u1 stuff, which has only, if you wish, like one complex number or 2 real components, as we'll see in the next slide. So the point is, this is not same as space dimensions. Okay, so these indices here refer to the internal space of the system, and this is something that you must always keep in mind. It is possible that you can give them the meaning of space direction, but it's not necessary, and generically they don't they are not space directions. Okay, all right. So the next question is, now that we have identified what is a emergent field, which is an n component vector that can carry a representation of ON symmetry, how do I construct this L of phi? Okay, so this is the key question. All right, now you might wonder, oh, I have introduced ON, where n can go from 2 and greater than so on. But I made I started off the lecture by saying, look, the superfluids are described by U1. Now you may think, okay, shouldn't we think in terms of some UN or something, so that we can make direct connection to superfluids. So I will show you in this slide that U1 is actually morally same as no, actually more than morally same as O2, right, as you will see, right. So my point is, within our framework, if you put n equal to 2, we can study superfluids. That's what I'm trying to convey in this slide. Okay. So we have seen that the symmetry associated with superfluid transition is U1. So U1 symmetry is typically captured by an emergent complex field. Just a single complex number is good to capture U1 symmetry for me. How do I say that? So if you look at the elements of the U1 group, one simple way of representing them is by a unimodular complex number e to the I zeta, where zeta is some angle between 0 to 2 pi. So you can close this, and 2 pi can be identified with 0 whatnot. So how do they act on my emergent field psi? So what I will do is I'll take psi and multiply it by an element of the U1 group. So it will sort of transform that to a new complex number, which is e to the I zeta times psi. So this is how this U1 symmetry acts on my emergent field. Alright, now I'll show you that there is an alternate description to do describe this using O2 symmetry. How do we see that? So you can see that there is a map between this object e to the I zeta and 2 by 2 orthogonal matrices. So what is that map? So whenever I see this complex number e to the I zeta, I associate that number with this 2 by 2 orthogonal matrix, right? You just think about elementary rotations on two-dimensional space you have studied, real space. You will see that this is the matrix that you're very familiar with. So this is rotating by some angle zeta. Okay, all right. Now I have to make the identification of the complex number with now a two-component real field. So here is the two-component real field. So phi is phi1 and phi2. And what is phi1? Phi1 is identified with real part of psi, and phi2 is identified with the imaginary part of psi. Okay. So now you can see that the action of e to the I zeta acting on psi is exactly same as this matrix acting on phi. So my point is, the O2 symmetry action can now be described by this, which is completely equivalent to the U1 symmetry action with one complex number, or two components of or two component real vector, right? So these two are actually completely equivalent, and that is why I am saying that we will use O2 to study superfluids, right? So our formulation will work just as well. Okay. All right. So with that discussion of how to describe the emergent field, and the fact that our discussion is motivated by superfluids and magnets with continuous symmetry, etc., we will now go on to discuss how to construct the Landau theory. In other words, how to find a Landau function. Okay. So the emergent field, as we have agreed, is a vector with n components, and all the components are real. And under the symmetry transformation, this phi will go to R acting on phi, R as a matrix acting on phi. And important thing to show is to observe is the following. If you take phi dot phi, now this dot product is dot product in the internal space. So what do? I take something, if I want to write in matrix form, I take phi transpose phi, and that will give me, in using summation conventions, sum over all components. So if I have two component vector, it will be phi1 square plus phi2 square. That is what this is, right? And you can see that this object is invariant under the ON symmetry transformation. This you know from elementary geometry, right? So for example, if I take a vector in two spatial dimensions and I just rotate it, then I know that the length will not change. So that's exactly what this is. So this is just saying that length is invariant under rotations, is exactly that. But I invite you to just formally prove this using properties of this orthogonal matrices, which we have quoted in the previous slide. Okay, all right. Now, before we proceed, I just also want to flash some notation that is very commonly used in this literature associated with these class of problems. So when someone says a vector square, what they mean is phi dot phi. And when they say vector to the 4, what they mean is phi dot phi the whole square. Okay, so this is typical notation that people use. Okay, so I'm now ready to write down the ON symmetric Landau theory, and with all the background that is given up here, you will see that the Landau function that I'm choosing depends on two parameters, actually a single dimensionless parameters, and there are two other constants here, which as we had discussed in the last lecture, you can choose them to be 1 if you wish, but you can hold on to it if you want to play with some dimensions later on. Okay, so this is the Landau function. So let's see what we have. We have some quantity which we can tune. This is what we call as t. This could be our distance to transition. And then there is phi square, which is of course invariant under ON rotations, and b by 4 phi to the 4, which is also invariant under ON rotations, and this is the very simple way of generalizing what we did for the Ising model, which is phi square plus phi to the power 4, where those were numbers, now these are vectors. Okay. All right, so this is our Landau function. So we also would like to apply some symmetry breaking fields. Now what are symmetry breaking fields in this context? So in the ON model, the symmetry breaking field will also be an n component vector, right? So if I take some n component vector, that can act like a field, symmetry breaking field for me. And this n component vector again is written as h, and we used to use h tilde to say it's dimensionless coupling constant. So from now onwards, we'll agree that when we say h, we mean dimensionless coupling constant, so that we can do away with the extra baggage of this tilde notation, right? So we have this, and h alpha will go from 1 to n. So it's some n component vector. It picks out, if you wish, a direction in the space of our field, in the space of the phi field, and the direction and its magnitude will describe this magnetic field, right? All right. So if I have an external symmetry breaking field, then my Landau function gets modified in a very natural way. So I have the Landau function when I have symmetry minus the symmetry breaking field dot phi, right? So this is also a nice number. It's dot phi. So that will be h alpha phi alpha using summation convention. This is the dot product of h and phi in the internal space. So this is my nice Landau function. Now Landau's simplest approach is to neglect all fluctuations and say that the observable order parameter or expectation value of this phi is what occurs when this L is minimized with respect to phi for any given set of parameters, and that will give us that the M, the order parameter field, which is the expectation value of this phi field, that will be that will satisfy this equation. Okay, so this is a very straightforward derivation. You can just take component wise. If you take a derivative of this with respect to phi alpha and just work through the algebra associated with this, you will get this equation. And then once you know that the equation is true for a certain alpha, you can elevate it to the vector notation without the crutch of the indices, and you will get a very nice expression like this. Okay, so please do this. In case you want to pause the video and take a shot at that, please do so. Make sure that you understand all the technical aspects as well. Okay, all right. So what I'm going to do now is I'm not going to have any external symmetry breaking field, and I want to study the system in the absence of any symmetry breaking field to see whether there are some nice phases I can get, even phase transitions, right? Okay. So the main message I want to convey in this slide is that the Landau function has very different character when t is positive as opposed to when t is negative. Okay, so let's see what that is. So when t is greater than 0, I am showing you two plots here. There is a 3D plot. So these plots are done for O2 model. Of course, it's very hard to draw anything greater than 2 because we can't project anything from higher dimensions onto here without getting confused ourselves. So, okay, so we'll just work with O2 model, but all the math, everything works out same for even any n greater than or greater than 2. So what happens here is when t is greater than 0, if I look at this L of phi and plot the L of phi in like a surface plot here, you will see that it looks like a paraboloid I should say, with a minimum, which is, I hope you can see this little red dot here, at the bottom of this thing. And what is shown here is a contour plot of the same function, and this red dot is the point where L is getting minimized. So what it's telling you is that the value of phi at which this Landau function is minimized in the absence of a field when t is positive is phi equal to 0. So that means that the system will not have any spontaneous order parameter, so the value of the order parameter will be 0, and you will be in a symmetric phase. That is what it's telling you. Okay, very good. What happens at t equal to 0, you will see, is something very interesting. You can see that this paraboloid has flattened out. It has become a flatter vessel, if you wish. So it's got a like almost a horizontal touching on the floor here. That's the 0 plane. The light gray shaded thing is the 0 plane, and you can see that the minimum is still at 0, and therefore the order parameter is also 0. Okay. So the most interesting thing, of course, is what happens when t becomes negative. So let's go to t equal to -1, and now you see something spectacular has taken place. This energy function now has a local maximum at phi equal to 0, and it has a structure which is called as a Mexican hat, right? So this is typically called in the literature as a Mexican hat structure. So you'll get a structure like this, and there are many possible values of phi, all of which lie on this ring here, which have the lowest energy. And you can see that this energy now is below 0. See, that's the 0 plane here, and this energy has gone below 0. Here the minimum energy was always 0. Here the energy has gone below 0, and the value of phi at which the minimum energy is attained is not unique. It can be anywhere on this ring, if you wish, right? And you should not be surprised by this, because the system has O2 symmetry. So if I have a phi where energy is minimized, if I hit an O2 transformation, right, it will go to some point there. The vector will rotate that way, and it will go to some point there like this, and that should also have the same energy, and therefore you get this ring. So what will happen in O3? In O3, you will see that the minimum energy will be a surface in the phi space, and it will be actually the surface of a sphere, right, and so on. So this red curve are all possible minima of the Landau function when t is less than 0. Okay, so what is it that we can infer from this discussion? What we can infer from this discussion is, you can obtain the magnitude of the order parameter. What is the magnitude of the order parameter? It's the length of the phi which minimizes the energy, right? And that will satisfy the following equation. This is very straightforward. It follows from it follows from this equation actually. It follows from this equation. Put h is equal to 0, and you know that m is not 0, so it's a plus b mod at plus mod m square, that is 0. So from here you will find that there is a non-trivial solution when t is less than 0, and that non-trivial solution for magnitude of m goes in this fashion as square root of t. So immediately, with very little effort, we have discovered that the critical exponent corresponding to the order parameter, which is beta, is 1/2, and this quantity C beta plus by C beta minus is 0, because there is no magnetization for t greater than 0. So here is a very important thing you should remember. The Landau theory will only provide for you the magnitude of the magnetization. It will not provide the direction for you. It cannot provide the direction for you because the theory is ON symmetric. So which direction will be chosen? That will be picked spontaneously by the system depending on what conditions it came to the symmetry broken phase. So what you will find, if I have let's say that you have a system with O2 symmetry, or O3 symmetry is more easier because this can be done with magnets and so on. If you cool the system down below Tc, then you will find that the magnetization appears in some direction. if you keep doing this many times, if you do experiments many times by removing all the external fields and isolating the system completely and all that, then you will find that the magnetization can appear in random directions. And if you do lots of experiments, you will see that it will appear pretty much anywhere in any direction with equal likelihood. So this is telling you that there is an underlying O3 symmetry in the problem, and this is very analogous to what we found in the Ising case, where you could get plus magnetization or minus magnetization with 50% chance. Here there is a continuum of possibilities of directions of breaking symmetry. So all of those are equally likely. The system will pick one of them. How it does so is probably by some chance, but that's what it does. Okay, so the theory can give you only the magnitude of the magnetization or the order parameter. It cannot give you the direction. It should not give you the direction actually, in the absence of any external field. Okay, all right. So once I have this mod m, we know that the free energy is simply the Landau function computed in this approximation of ignoring fluctuations, is simply the Landau function evaluated at phi equal to this m, right? And you will see that the free energy can be extracted to be this, which will imply that the specific heat has a jump discontinuity at the transition, namely T equal to 0. So that is the statement that is shown here. It has a jump discontinuity. So this is also what we found in our analysis of the Ising problem. Okay. Now what we will do is we will discuss what happens when the external magnetic field is non-zero. Okay, so what do I have to do here? So you have to understand what I am doing. When I say external magnetic field is not zero, what am I doing? I am saying that I am equilibrating the system in the presence of an external magnetic field, right? So this is, you have to understand that this is different from starting from a system with zero magnetic field and looking for susceptibility, which is turning on a magnetic field, which we will do in the next slide. Here we are studying the system which has equilibrated. It's a field cooled system, if you wish, right? So in presence of this magnetic field, the solution of M, okay, will satisfy this equation which we have seen before. Now if you look at this equation, you will see that this is a vector, and AT times B mod M square is just a number, and so M will be in the same direction as H. So what this tells you is that within this theory, M will be always in the direction in which you had the field on. Okay, all right. Now if you find out what is the solution for M, now what I'm doing is I'm taking the O2 model and I'm applying H in the one direction. So I have only H1 here. So you can see when H1 is positive, this light color here are positive numbers and the dark color here are the bluish colors are the negative numbers. So you can see that when H1 is positive, M is also positive, and M will be in the same direction as H1, and you will see this result like this. Okay, and so you will see something and you may think that, oh, this looks very much like the Ising model. It does, but there is a subtle difference, as you will see. Okay, so when H is positive, if T is greater than 0, then of course you can go smoothly, and if you go like this, you may think that there is a first order transition, but that's not the full story here, right? So remember that you can also have H2, the other component. So what I'm showing you here is, this is the critical point in the T H1 H2 space, right? So there is T, the distance to the transition, there is H1 component and H2 component. This plane here is the H2 equal to 0 plane, right? So that's what it is, and so that's same as this plane that I plotted on the left side here. Okay, so now imagine that I had this magnetic field H1, which was some small positive quantity here, right? So I have a positive magnetization. So in the Ising case, suppose you want to keep T negative and fixed and reduce the magnetic field and go negative, then you would come down this way and you will encounter a first order transition. But here you don't have to encounter any transition in going from the positive H1 to negative H1. What is the trick? The trick is you can actually do an excursion in the H space. So you turn on a magnetic field. So the magnetic field was turned on in the positive H1 direction, and this is negative towards me is negative H1 direction. So that is positive H1 direction, let's say. But what I do is I don't reduce the magnitude of H1 alone. What I do is I rotate this H magnetic field. Okay, I rotate it, make it into H2, and then come back to negative H1. So you can do an excursion like this, which avoids the H equal to 0 line, and you can go from this side to that side without encountering any first order transition. Okay, so that's the new aspect that shows up in the system with continuous symmetry. So in the discrete case, you didn't have this extra magnetic field you could apply, or the magnetic field didn't have enough components, if you wish, and therefore these two symmetry broken phases were separated by a first order line. So here they are not separated. You can actually they are continuously connected, right? So that's this gray line that I'm talking about in sort of which describes the physics I just indicated to you a moment back. Okay, so that is the H not equal to 0 story. Okay, let's explore a bit more. So can we extract other critical exponents? So we can now look at the susceptibility. Remember, when we talk about susceptibility, what we are doing is we are keeping the system, the equilibrium state of the system has no external field. So you have a system which has, if it has broken symmetry spontaneously, it has picked some direction, and there is some state that is there. You are going and applying a magnetic field as a perturbation on that state to see what the response is. Okay, so this is how susceptibility is usually defined and calculated. So what I have is I have an equilibrium system with a spontaneous order parameter m. So this has been calculated already, given t, etc. It has been calculated, and now I am applying an external field, right? Okay, external this symmetry breaking field here, and we want the response delta m. So remember, this is different from what we did in the previous slide, where we equilibrated the system in presence of the field, right? Okay, so what should I do here? So I will say that the change of m is delta m, and I will write down the same equation with this result here. Now if I want linear response, I will expand these terms to linear order, and you will end up getting this equation, which is a fairly straightforward thing to do. So I will not go into the details of the math, which you can work out yourself. Okay, so now I will point out to you that the story from here onwards is somewhat different from what happens in the usual Ising model. So you will see that there are two cases here. So imagine that you have a system with spontaneous magnetization m. Then there are two things you can do. You can apply the field H in the direction parallel to the order parameter m. So H is parallel to the order parameter. Okay. So if I do that, then you see all of these things are parallel. So you can just forget about the vector quantity here, because all of them are in the same direction. And you can see that this problem will reduce exactly to the problem of the Ising kind of system that we studied, right? And then you will find that the susceptibility, parallel susceptibilities, parallel meaning parallel to the direction of the order parameter, will turn out to be 1 by AT when t greater than 0. So here there is no meaning for parallel because there is no order parameter. So but that's okay. So we will see that that's just 1 by AT for t greater than 0. And when t is less than 0, you will get exactly what you found for the simple Ising case. So the parallel susceptibility looks exactly like the Ising case. So it has a critical exponent of gamma equal to 1, and C gamma plus by C gamma minus is the amplitude ratio, which is 2. Okay. Okay. What happens when H, so let's say that this is the magnetization direction, and I apply a field perpendicular to the magnetization direction, right? What happens is that if t is greater than 0, then this problem doesn't care whether it is parallel or perpendicular. You can just see that from here, right? Because all this mod m square is 0, this whole term is 0, so you get at delta m is equal to h, and then delta m will be just parallel to h, and you will get exactly the same susceptibility for t greater than 0 that we saw. But what you will find is, when t is less than 0, then I invite you to do the analysis in detail. You will find that the linear response calculation will not be quite right. Right? You will not be able to pull off the linear. If you try to write down the linear response relation, you will get some garbage. You will see something 0 is not 0 and so on. So you have to keep the nonlinear terms as well, and then you will find that you will see that the delta m is sort of proportional to the perpendicular magnetic field to the power 1/3. So if that is the case, if you simply take the susceptibility, which is the derivative of delta m by h, you will see that will diverge, right? So that is the point. So when in the zero field limit, that will diverge, and so formally we can say that the linear susceptibility is infinity. Now you may find, oh, that's a little strange, right? I mean, how can you get linear susceptibility is infinity? But that's actually expected, and you should have anticipated this. So let me explain to you where that is coming from. Okay, that comes from this Mexican hat structure. So you see, this is the energy profile, and let's say that my magnetization was picked up. The spontaneous magnetization was picked up along the x-axis here. Now, if I apply a magnetic field in the perpendicular direction, it's quite natural that the spin can just move into, so it can just rotate and align itself with the direction of the magnetic field and gain a lot of energy, I mean magnetic energy. But in doing so, it loses no energy to this to the Landau function, because you are not changing the magnitude of the magnetization, you are just rotating it. So you will see that you can gain a response by paying no extra cost to the Landau function. So that is why you are seeing an infinite susceptibility. So it's like a soft mode, if you like, and we will see that this has some very important consequences. We will come back to all this later. So you will see that this leads to what I call gapless modes and all that. So we'll discuss that in the coming lectures. Okay, so this is the result, and so you will see that this is one new aspect of what happens when you have continuous symmetry. When you have continuous symmetry, the response in the broken symmetry phase has some more structure than in the discrete symmetry problems. In continuous symmetry cases, you will get a finite Ising like susceptibility if you apply magnetic field in the direction of the order parameter, and if you apply a magnetic field in the direction perpendicular to the order parameter, then you will get infinite like response. That means that you will have huge responses to magnetic fields perpendicular to the order parameter. Okay, so we can also complete the story by looking at the critical point. So this is the t equal to 0 point, and there by a very simple calculation, again just put m equal to 0 and put at term equal to 0. So you will see that this equation simply becomes b times delta m cubed morally is equal to h, and the directions will be the same because there is a mod m here and delta m and all of that stuff. And so you will get that the magnitude of delta m itself will be parallel to h, and the magnitudes will be determined by this, and which gives us the critical exponent delta equal to 3. Okay, so this is the result of Landau theory for On, and so in a sense for all n we have solved the critical properties using Landau theory, and this we did in the last half hour or so. So you can see that this is actually an extremely it's a very simple exercise from the math perspective, but it provides you all this nice results. We have to check whether they're correct or not with experiment. We'll do that in the subsequent lecture, etc. But we do get the results. Okay, so I have to tell you some more exciting things about continuous symmetry. So we used continuous symmetries, and we said there is a we can write down Landau theories for continuous symmetries, and we chose the emergent fields as vectors and so on. So I'll show you that is not the full story. You can do much richer things, and you have to do it, and it'll actually explain experiments. So let me show you quickly. I have to tell you that I'm not going to go into the details of the technical details of what I'm going to show you. The idea is to illustrate for you some conceptual ideas that are necessary and useful when trying to apply Landau theory to a variety of problems. Okay, so very early on in the course, we had looked at what are called as nematic systems. So what happens here is you put together a bunch of longish organic molecules, longish meaning that they look like rods, right? They look like rice grains, if you wish. Okay. And so what you can do is you can create a system where all these molecules are interacting and they are sort of fluctuating thermally and so on. So if you are at very high temperature, above some transition temperature, they are in what is called an isotropic phase, right? So they are all oriented randomly and all of that stuff. So if you were to write some energy function of something like this, this problem will have some kind of rotational symmetry. The rotation will act on this rod and it will rotate it in whichever in any three-dimensional rotation you can do on this. So what is found is that if you reduce the temperature, so in this experiment, you see that about 35 degrees, there is a first order transition. You can see that the order parameter suddenly increases in a span of very little temperature change, and then it sort of grows up. There is a first order transition from isotropic to what this phase called as a nematic phase. So nematic phase means very simple. If you look at the center of masses of each of these rice grains, if you wish, or these longish organic molecules, they are not ordered in any way. They are fluctuating any which way they want. But the orientations of these these longish molecules, they have all aligned themselves in a certain direction in space, and the direction is spontaneously chosen, right? And so this is the symmetry breaking that we are talking about. So naturally, the symmetry breaking is something associated with O3 rotations. But now we are immediately running into a problem because we constructed a generic O3 Landau theory, ON in fact, and we saw that the way we constructed it, when we tuned the parameter in our problem, you had a second order transition. So how come here generically in variety of such crystals, liquid crystals, and these such longish organic molecules, generically you will find first order transitions. So you should be puzzled by this, right? Because this is sort of not agreeing with what we did. We said O3 symmetry, we can use a vector and we can get the answer. So it's a good time for you to pause the video and try to see whether you can crack this problem yourself. How can we get a first order transition generically? Okay, so I'm going to proceed. So after a lot of thought and many smart people worked on this, they realized that the organic molecules that are this way should be thought of as headless vectors. What do you mean by headless vectors? So imagine I have a rice grain. The rice grain, if I sort of, so think of them as long ellipsoids. So the direction of the ellipsoid, it doesn't matter which side of the ellipsoid is pointing in this direction, right? So it's headless. It's only the direction that matters. And the direction chosen, the direction cosines are this. So it doesn't matter whether you're pointing the vector that way or this way, they're equivalent. That is what we mean by headless vectors. But our three component objects, which I would have done for O3, is a head full vector, right? So it's not good idea to have too much of headfulness, then you will not be able to do things, right? So that's what's going on here. So the object that we are calling as the emergent field is not the right description of the kind of emergent field that we need here. Here we need a headless vector for the emergent field. Okay. Now without getting too much into the details, I will just make the statement. You should try to think about why this could be true. Such a headless vector can be actually mathematically described by a second rank symmetric tensor which is traceless. So I'm writing this as Q here, and it's a 3 by 3 second rank symmetric tensor which is traceless. So that means in the notation we have introduced Q alpha alpha, which would be the trace of this 3 by 3 symmetric matrix, would be 0. The claim is that this such an object describe an emergent field of headless vectors. Okay. Now, why this is the case, etc., I will not have time in this lecture to discuss. So, you can think about why that would be the case. Okay. So, the first thing is we have identified the emergent field as this second rank symmetric tensor. What is the next thing we should do? We should try to see how does the symmetry act on this. So, I know that O3 objects are described by 3 by 3 orthogonal matrices. How do they act on this? They act exactly as how 2 by 2, 3 by 3 orthogonal matrices act on second rank symmetric tensors or second rank tensors. So, the way it would act is Q alpha gamma goes to two so it's something like if you write it in the matrix form, it will be like R Q R transpose something, or R transpose R Q, R transpose Q R, whichever way you like to think about this. So, this is the way it will actually transform. Okay. So, with the way I have written this, it will be R Q R transpose. So, that is what it will do, and this is the way it will act. Okay. So, I have this second rank symmetric tensor. So, under the action of this R, it will get it will get rotated into some other second rank symmetric tensor. Okay. So, what is a Landau invariant theory for this? So, remember, if you think about variety of things that you have studied before, you will see the trace of any matrix is invariant under these such orthogonal rotations, right? Trace of a second rank symmetric tensor. So, you will see that in fact trace Q square and Q cubed, all of those are also invariant. So, those are terms that we can use in our Landau theory. So, the Landau theory has three terms that is written down here. AT, T is the distance to the transition, trace Q square, B trace Q cubed, and G trace Q square the whole square. So, now the very important thing to observe is that you are forced to write this, because this is, see, we could not write phi cubed term in the Ising model because it was not invariant under symmetry, but this is invariant under symmetry. You can explicitly show that trace of Q cubed is invariant under symmetry. Okay. So, you have to write it, there is no choice. Now, you may wonder why am I having this term? Okay. If I stop at Q cubed, then you see, so this morally looks like phi square plus phi cubed, but that kind of a function has a problem, because if you go one direction, so if phi becomes very negative or something, then phi cubed is very negative, and so there is some there is no lower bound of energy, it can keep going down. So, if you stopped at Q cubed, then this function does not have a lower bound on energy, so you don't want unphysical things to happen. So, you know that you have to have some function which will prevent that. So, this is always positive and it will grow when the magnitude of Q grows. So, you have to hold on to this so that your energy function has a lower bound on energy. So, this is, by the way, very important condition that you have to use when you write down Landau functions. They should have some lower bound on energy. They should not have negative infinity is the lowest energy state, should not should not show up there. Okay. So, this is sort of forced on you by the structure of the theory, and the most important thing is you will get this Q cube term. Okay. Now, you can show yourself, okay, if I had a Q cube like term, the transition will be generically first order. Okay. So, you can see that this is a remarkably beautiful result, because by just identifying the order parameter and noting that this kind of term is unavoidable, we are forced to conclude that the transition is first order, and which is exactly what is found in experiment. So, you can see the Landau theory is extremely powerful in capturing a variety of physics that we see around us. Okay friends, so we have discussed quite a few things today. So, it is a good time to summarize. So, the world around us is full of examples with continuous symmetries. So, you have superfluids, magnets, liquid crystals, whatnot. So, what we try to do is we try to study phase transitions in systems with continuous internal symmetries using the ON group, so that we can attack all these problems all at once. And we introduced and studied in detail the ON vector Landau model, and we briefly mentioned the ON tensor Landau model at the end of the lecture, right? And where the emergent field is an n-component real vector phi, and that transforms nicely under this ON transformation. So let's quickly revise the main results that we got from Landau theory for the critical properties. So the first result is that the specific heat has a jump discontinuity. Second is that the order parameter critical exponent beta is half and the amplitude ratio is 0. Third result is that the susceptibility critical exponent gamma is 1 and the amplitude ratio is 2. And the critical response at the critical point has a critical exponent described critical exponent delta, which is 3. Okay. Now comes the most sort of interesting observation. So all of these results are true for any n. So whether it is n equal to 1 for the Ising system or for n equal to 2, 3 for continuous, they are all the same. That's the first observation. And second observation is they don't seem to depend on spatial dimension d. Nowhere in these things spatial dimension is showing up. So this is what we find, right? Okay. So in the next lecture, we'll take a closer look at these results and see what happens. We'll realize that there's something missing here or that we have to do something more. And we will do some extra things there, and we'll also address. Remember that when I talked about the superconductor, there was a phenomenon where when I passed current, there was a critical current after which superconductivity died and you went to the normal state. We will show that trying to repair these things can also be useful to study this, this kind of a phenomenon. So I'm sure that the course is getting more interesting with all these exciting new results that we are finding. So please join me for more discussion on these things in the next lecture. So have a nice day and see you.